Hey algebra students, today we are on lesson 13.4, comparing linear and exponential models. Starts on page 647, but we are actually going to skip over to page 649 and start with the explain part 1 because our focus today is on comparing linear and exponential functions. When we're comparing raises at a job, for example, this is our real world context, if you're getting a fixed dollar amount increase every month, that would be a linear function because that's a constant rate of change. However, if you get a fixed percent increase each month, that would be an exponential function. We've seen percent increase and percent decrease when we did exponential growth and decay, and we had our growth rate was typically a percent, or our decay rate, and we had to change it to a decimal and all that stuff. So when we have a percent increase, that is exponential. So they're asking us in this example to compare the two salary plans from job A and job B on our graphing calculator, and they want us to figure out if job B will ever have a higher monthly salary than job A, and if so, after how many months does that occur? In the real world, this is information that you might take into consideration before accepting a job. If you are offered jobs at multiple companies, this might be something to consider. So for job A, we start with $1,000 for the first month, and we are promised a $100 raise every month thereafter. So that $100 every month is a linear rate of change. And so we can write this equation that Y, our salary, would be $1,000 to start, and we would add to that $100 for every month after. I'm going to put T for time since months are a unit of time. For job B, we would get $1,000 for the first month, and then we would add to that a 1% raise. Remember, 1% is 0.01. So as we saw with exponential growth, that growth rate was 1 plus our rate. And again, if you think about it, we are going to be, we're getting a raise, so we're adding to it more than what we started with. So we would actually multiply here times 1.01 to the power of t, our months. This goes back to that y equals a b to the x exponential function. Or if you want to go back even farther, the exponential growth function of a times r plus 1 to the x. Okay, so these are our two functions. We are going to plug them in, and they are actually already given for us down here. We're going to plug them into our calculator in the y equals screen. So the first one is 1,000 plus 100 per month. The second one is 1,000 times 1.01. That's a 1% increase over, if we think about it, if we multiply 1,000 by 1, then it would still be 1,000, and we wouldn't have increased our salary. So that's why that 1% is added on to the one whole, to the power of x. Let's take a look at our graphs. You may have to adjust your window or your zoom in order to see the two graphs at the same time and in order to see where they are going to intersect. Yeah, see, mine are not going to show up on this. So I'm going to say zoom, and I'm going to go to zoom fit and try that and see if that works. Calculator's got to think about it a little bit harder. This should be the one that we see on the textbook pages though. Nope. It's going to zoom out even farther. So you can play with your window, but this right here is what, if you would keep adjusting your window to get them both to show up, this is what you're going to see. You can still use that calc trace feature like we did when we were solving systems of equations to find this point where they would be the same. And in this particular instance, you would find that at 364 months, the salaries are equal. After 364 months, then the exponential function would be higher. So at that point, job B would be the higher salary. So let's try another similar question on page 650. So on 650, we're going to skip down. And by the way, up here, it shows you how to use the table to find that point where they are the same and changing which one is a better pay. All right, so job A in this situation, in example B, is $1,000 for the first month with a $200 raise every month after. So that's our linear example. Job B is $1,000 for the first month with a 4% raise every month after. That's a percent raise, so this is our exponential function. And so if we write our equations, for job A, we're starting with 1,000 and we're adding to that 200 per month. That's what the T is for. For job B, we're starting with 1,000 also, and we're multiplying by 1.04. Again, that's the 1 plus your growth rate that we learned in the exponential growth lesson, to the power of T. So let's go graph these on our calculator. 1,000 plus 200x is our linear, and then 1,000 times 1.04 to the x is our exponential function. And we'll see if these two fit. If not, we can use Zoom Fit to make both graphs appear. We're really close, so let's try Zoom Fit. Let's see if we can get both of them on here. I don't think that's going to work. So we can adjust our window, or we can continue to play with different zooms. Oh, look, we can see the intersection right here. So if I do second calc, intersect, I'm going to hit enter, 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 and there's our intersection. When X is 68.54, that's months, then the two jobs are about the same salary. So at about 69 months, we'll go ahead and round that, the salaries would be equal. So then after 69 months, job B has the higher salary than job A. So then let's look at the reflection questions. In example 1A, the first example, which job was a monthly salary that was a constant change? That was job A, because it was linear. And then which one reflected a constant percent change? That would be job B, because that was the exponential. Okay, so let's go ahead and let you try one down here, number 6, and we'll see what you come up with. I'm going to work it silently so you can follow my process, or you can pause it here and try on your own and then go back and see what I did, see if it matches what you do. I think I'll actually talk through my process here. So for job A, $2,000 for the first month with a $300 raise every month after. That's linear, and notice we're starting at different starting salaries this time, but job A is going to have an equation, y equals 2,000 plus 300t. Job B would be y equals 1,500 times 1.05 to the t. And let's plug this into our calculator.
Staff, if you may have left your phone in the restroom down here in the front office, we have it in the office. Thank you.
So many fun announcements when we were recording videos after school. To the x. Okay, going to see my graph. Let's see if we get lucky and our window is, oh good, our window shows us the intersection. So I'm going to do calc trace, second calc, intersection, enter, enter, enter. All right, our intersection is when x is 49, almost 50, and y is 16,886. So at about 50 months, the salaries would be equal. And after 50 months, for example, if I look down just a little bit farther, B, job B, salary B is higher than salary A. So after 50 months, job B's salary is higher.